All right, welcome everybody. We will move forward with what we did last time. This is the terahertz or T-ray workshop. As at the very beginning we said, is the A to Z of T-ray usage, application, and more importantly, nanometrology applications. So we divided the whole thing into two parts. First part is the imaging. Once that is done, then we'll go to the second part, which will be spectroscopy, time domain spectroscopy. Both of them are important for metrology, nanometrology, but more than metrology. There are a lot of other applications. So here today we are gonna continue from what we did last time, and more importantly, the examples of imaging is the main thing we're going to do to the practical examples and comparison with other techniques. It's, when you're doing imaging and metrology, measurements should match with other techniques, but difficulty happens when new kind of measurements are done and other technique couldn't produce that kind of results. So nonetheless, as they say, rose in any name is a rose, right? So the measurement should be, no matter how we do it, the measurement is right, it should be the same. So here are a few examples of different kind of measurements that were done. Not just that it looks pretty, the more important thing is that we do the measurement with these images. So on the left is an alumina. Alumina is an amorphous material, but what we saw here is that it has nano grains, and each of the grains have kind of their own crystal structure, but none of the grains have the same crystal structure. So it's kind of amorphous, and that's why it is an amorphous material. And this one is the nanocellulose. This color rendering can be different, and when we go to the practical software usage, you will see that color rendering, just to give it a look, it does not change the structure of the material. The material is material, what you measure. So, so here's again, it's a repetition, but instrument details, how the instrument is organized. The whole instrument has mainly three segments, three components. One is the main unit of the box itself. Then it needs a nanoscanner with X, Y, and Z axis, physical X, Y, and Z axis. And then, of course, you need a computer to do all the manipulations. And this is how they are organized. The central box, which is the main unit, are connected with all the things. And finally, they are connected with the computer. And, two-step process is done for imaging. So all the softwares that are required are always installed in the system. And users they need to be familiar with the usage of those applications or software, but then none of them are very, they are pretty user-friendly. But it still need to be, get familiar with it, need to use it and, get used to it, get a hang of it. Here are the app examples. Again, the apps they don't look very professional, etc. So we have mainly focused on the functionality of the instrument, applicability of it, as opposed to making the interfaces pretty and things like that. That probably subsequently will be done. But main structure of the software is that first we use the apps for this one, for the scanner operation. But the scanner operation is not all the scanner operation. Each app needs to access the scanner and operate it in their own way, as you will see. If we have a sample mounted on the scanner, then where do we scan? This kind of apps are used to find the suitable places where we do the scanning. Here is an example. After you've done the scanning, how does the scan data look like? And this is graphically displayed as we do this scanning, just for, it's not that this is going to be very important, but just to give it a look and feel that it actually is doing something. Otherwise, we have no way of knowing that it is doing something. This, the scan that you see here is corresponding to a whole patterned wafer, 200 millimeter wafer that was patterned with all the, dyes. And dyes subsequently become the chip. So this was, and this is how the profile as you scan look like. The software does tell you how long did it take scanning to scan the whole thing after all the scanning is done. So it could also, there's a version of software that also gives you the time budget before you start the scanning. Some scan may take really long. We have scanned samples for 2 days. But that's very specialized kind of scan. Here's another example that is a hard disk plater that was mounted on the scanner and image was taken. And if you draw a line, these all softwares are available, built in, not built in, but provided. You draw a line like this, and then you get this kind of profile. And this profile can be used for roughness measurement. I could measure the roughness somewhere else or anywhere. You will see as we go into the practical example. I'm showing you the real manipulation of the data. And the scanning resolution are controlled. I don't know where did this thing come from. Oops. Sorry about that. This is some leftover. Oh my God. Yeah, very good. Okay, so scanning resolution or image resolution depend on 3 things. One is the scanning resolution as you measure on the scanner. An image grading resolution, which is shown over here. And then image rendering resolution, which is a little bit different thing. So, the software gives you the opportunity to get things just right. Different thing requires different kind of, management. For example, this image you see, if you have a grid size of 50 by 50, for example, and on the z-axis grid size is not shown here because that's not being changed. So you get a very rough image. When instead of 50 by 50, we use 20 by 20 gridding, 200 by 200 gridding, it shows the structure a little bit better, and so on. So starting from 50 by 50, if you go to 2000 by 2000, the image details become very, very clearly visible. Only thing is, higher this grid number, longer it takes for the image manipulation or image generation. So a lot of times it becomes necessary to do that. A lot of times, if you are measuring a macro item, then we probably don't need that much resolution. For example, here, this is only 1 micron by 1 micron by 1 micron, but this required a lot of calculation. And this is a seashell structure, as we can use that image, one side of that image, to calculate the lattice spacing of where the crystalline areas are there. The crystalline areas where lattice structure are clearly visible. Amorphous areas are this one. There's not much crystalline structure, there. So this gives us a way to measure all the things that we need to measure of a microscopic object. The measurement technique is that we first make a, these line patterns are grayscale digitization, looks like that. So the black and white lines, white gives 256 point and black gives 0. That's how it is. It's called grayscale profile. And then there's technique called full width at half maximum, which is a very common technique that is used to calculate the lattice spacing from this grayscale profile. A practical problem, again, this is a repetition, we did it last time, that lattice dilation and embrittlement. Embrittlement is a big problem for all metallic objects, but embrittlement starts very beginning of that is the lattice dilation. That means the lattice structure separates, lattice spacing keeps separating, and eventually, this is some other problem. This is a nickel and ceramic interface, which is what we had to prove. And then we take lattice image and we see that lumina are embedded in some places. Then we isolate. So this is 1 cubic micron. And if we take only 100 by 100 nanometer by 100 nanometer by 100 nanometer from suitable places, then we can measure the lattice structure or lattice plane separation. So this is how we isolated one surface of that 100 nanometer cube. And then again, the same technique. We, take a line across the lattice plane that shows the intensity distribution, or as you call profile map, and then use the full width at half maximum to calculate the lattice spacing. And in this case, we found that the metallic nickel lattice has expanded because of the applied electric field. These are also spray deposited. So spray deposition did one thing, and on top of that, high electric stress caused the lattice dilation. Once we calculated the lattice, dilated lattice spacing, then we can also calculate their density. And as you can see from metallic nickel, whose density is 8.863 gram per cubic centimeter, that lowered and lowered as the lattice dilates further and further, the density falls proportionately, which is what it's supposed to do. So this is an important technique for getting the lattice dilation measurement of, we did nickel, but it can be for anything else. In nuclear industry, nuclear reactor, they have a lot of metallic objects in the reactor itself. There they can use this kind of technique as well for measuring the dilation. Other imaging example for metrology. So this is an example from the 3D packaged chip. These days the chips are not a surface device anymore. They are multiple, patterned, being stacked on top of each other, and the final packaging is done for space saving. However, this technique is not all that, initially people thought that this could be a very useful technique, but now instead of stacking the separate chips on top of each other, they are doing lithography in 3 dimension. So we'll come to that later. But this is an example to show that, these are this is on the left is an SEM picture. So we have measured the dots, their size and their separation. So the SEM image shows 2.7 or 2.5 or so micrometer separation of these dots. We come close to 2.7 micron. So this is within the experimental error limit. But you can see clearly where the dots are. Not all dots are equally separated. Some dots are closer than some others, which is also they saw over here, but they see only one surface. How does it, goes into the thickness? That's another issue. There's on another chip, they had this metallic line embedded in the silicon wafer. So we had to measure the separation of those metallic lines and the thickness of each line, width of each line, and then how does it look like as they go deeper in the silicon. So as you can see, this kind of aspect ratio, these lines went few micron deeper into the silicon, but they are narrower on the top and wider into the bottom. And this happens because of the channel, inside the silicon, making the channel is not all that easy. But if we looked at only surface, then we would not be knowing how's the structure at the bottom. So then compare with other techniques, meaning that these are the data that came from SEM measurement, and this is what we measured with T-ray, and then we calculated the percent disagreement, how much is different. The percent disagreement is new value minus the SEM value over the SEM value. So, so this checks out that what the SEM can see, also T-ray can see, however T-ray sees the depth and thickness, etc. Now, silicon carbide is another important semiconductor. So, do you know what's the difference between just silicon and silicon carbide? Any thoughts? So, biggest thing is the silicon carbide has a bigger bandwidth compared to silicon. Why is that important? A bandwidth controls the voltage that it can tolerate. So silicon carbide can tolerate much higher voltage compared to silicon itself. Also, the other thing is the temperature. Silicon carbide will be functional at higher temperature compared to silicon. Silicon will give up a long time ago. So So those are the two, as well as the other thing is called the radiation tolerant. Three quantities, three very important quantities. One is the high voltage, one is the high temperature, and the third one is the radiation. So if you have a circuit inside a nuclear reactor, for example, where a lot of radiation there, is it gonna still work or gonna give up? Or you send a device in the outer space where there are a lot of natural radiations there. So the space shuttle, will it work over there or not? These are the kind of things where silicon carbide and gallium nitride. We'll talk about gallium nitride after this. So those two are very special semiconductor. Still you have to remember that still 99% devices are made from silicon. Cell phone, computer chips, amplifier, all different kind of things comes from silicon. So there's no alternative for silicon. But in some applications, silicon is not good. And then what is the alternative? Is the silicon carbide and gallium nitride. There are other semiconductors people have been working on. But silicon carbide has its own line of problem, own issues. And you will see some of the issues I'm discussing here. And those issues, those are the main issues why silicon carbide is still not a mainstream semiconductor. It's useful, but making devices out of it is very difficult. Why? Because silicon carbide is grown at high temperature. Compared to silicon ingot is made around 1400 degrees C or so. Compared to that, silicon carbide goes to 2200 degrees C and above. There's a significant difference and significantly high temperature. So the way the silicon carbide is made is called physical vapor transport. It's also called seeded sublimation deposition. So all different kind of names are there, but more commonly known as the physical vapor transport, or PVT, not D. Physical vapor transport, because what happens is we take the silicon carbide source, which is basically silicon and carbon. Both of them are evaporated, the sublime. They don't melt, they are evaporated. And then they go and deposit on the seed, silicon carbide seed crystal. So because of that process, these coils around them are the induction heater. So there is a temperature gradient. There is temperature gradient along the radius, also temperature gradient along the axis. Both of them has certain effect. And then the basal plane bending. As they grow, there is thing called basal plane bending. And there are more. This paper is from, I forgot to add the reference here. This is from the 90s. Somebody published this paper. So these images are borrowed from that paper, except for this rightmost one. This boule or ingot is the same thing, right? We call it boule, B-O-U-L-E, or ingot is the same thing. This boule then is sliced and individual wafers are made, the slicing and polishing. So what happens in case of silicon carbide, this boule length is very short. In silicon, it can be 2-3 meter long ingot. If an ingot is 2 meter long, how many wafer we can get out of that? Quite a few, right? If each wafer is 1 millimeter thick, for example, then you get 2000, but wafers are less than that. So per meter of the boule, you get 1,000 or more wafer from silicon. But in silicon carbide, these wafers are much thinner. These are only 350 micron thick. And even though that thinner, because silicon carbide is way more harder than silicon. So you can make much thinner wafer. Except the boule growth, here is only limited to 50 or so millimeter. You cannot grow a 1 meter long, 2 meter long boule in silicon carbide. Why? I mean, that's an issue. Of course, you can easily see that's an issue. But why? Because because of this boule growth process keeps some impurities, keeps some thing in it that subsequently do not allow for long boule growth. So what are those things? People don't know yet. One of the things that we have found when we do the T-ray image, as you can see on the right side, all different kind of patterns comes in that are not visible from other technique. So what are the other technique? Right now, the techniques are optical. This A and B are the optical image of the same wafer whose T-ray image is on the right side. So as you can see, the T-ray is seeing all the things that optical are not being able to see. However, some correlation are there. You see this shape here is there, except a lot more details seen by T-ray. This thing over here, since this is a mirror reflection, so it's on the other side, it is there, but this is the best all the modern technique can do. We also compared with X-ray, the same identical wafer, you cannot see much either. So unless we can fix all of these issues that are in there, that was not known up until now, the boule growth is gonna, suffer. So how do we know that what we see is real? Because we were lucky to get a number of wafer in sequence from the same boule. And when you put them side by side from all the T-ray images, as you can see, this pattern inside here is transpiring. So it must have come from what was in the original, ingot. So that's an issue that now they need to deal with, the industry need to deal with. I mean, when you do a scientific experiment, you have to be skeptic of your own. You must make sure that what you are doing is the right thing. We cannot deal with an artifact, for example. So what we did here is that we took one wafer, we did image in reflection, but we also make the same wafer image in transmission. So the difference is where in reflection where you see dark, in transmission you see bright because light is going through. I mean, T-ray is going through. So all the intricate things that we see here is not just an artifact. It is there within that material. That's proven clearly with this reflection and transmission images. And by the way, there is no instrument in the world that can make a 150 millimeter wafer image in transmission. So it's a tremendous advantage. And when we compare with silicon, the left one is a silicon wafer, 200 millimeter, and this one is 150 millimeter silicon carbide. As you can see, silicon came a long way, over over a century or so. So silicon has, whether by material itself or by perfecting the process, silicon doesn't have that kind of, crazy thing inside the wafer. This is the domain information, and then this is the lattice image of silicon carbide, from which we can see that there are a lot of nanograins as well, and the polytyping. That means what kind of silicon carbide has a lot of different crystal structures, polymorphism. So, and that becomes an issue. They have a pretty good control on H4, 4H, 6H, and R4, 4R, but but there are a lot more, so they have to make sure that they don't bring different kind of polymorphism in only one wafer. So all of these are nanograins, but they have the same crystal structure. So that's why they have the same, material. The other thing here is a slightly different issue now. Up until here, I don't know if you have any question or comments. So the other thing we're going to talk about today is called interface. As you know, the semiconductor chips, when chips are made, they are made in layers, a lot of layers, hundreds of layers. The way they do it, they put one layer on, they pattern it, then they have to put another layer and another layer of different kind, etc. It keeps on going. So the interface characterization becomes an issue. Interface is the space between the two surfaces. And ideally, what we want is that they should form very integral interface, no impurities, no defects, no crack or delamination. Those are the kind of things that need to be inspected, because if they are there, then the device will not work properly, or they will fail very quickly. So, so there are different type of interface that has been defined in the text. First one is called the misfit lattice interface. Type 2 is the identical lattice interface. Type 3 is the rough surface interface. And type 4 is the diffusion type interface. So when we have taken this image and looked at it very carefully, so this is a layer 2 is a kind of carbon material on top of which a different kind of layer was deposited. And below that, they have different materials. So now those interfaces can be seen clearly as well as characterized clearly. So on the right side, this is an example of the identical lattice type interface. Two material, but both of them have the same lattice structure. So they look kind of very same. But interface still can be seen a little bit of, interface is become visible. And the diffusion type interface is not shown here, but that can also be identified with this. So with that, let's stop here today. Next time we'll start this profile mapping of patterned wafer for yield enhancement.
One question about the slide. What is the quantitative value that compares each of these types? You mentioned lattice separation is a good one. But for these types here, how is a scientist to know that this layer corresponds to type 3?
Oh, More important, yeah, that's a good question. More important is the when they are depositing the material, they know what material it is. And so if I'm depositing, let's say, silicon and germanium on top of silicon, for example, right? There are examples of those. So then silicon lattice and germanium lattice are very close, not that much of a difference. But there are difference, but that difference can be quantified. What is more important here is that when they are depositing epitaxial germanium, let's say on silicon, is it, is it doing the same perfect match on one of the surface of the germanium surface on top of the silicon surface, for example? Those are the kind of thing they need to know, but they also need to know the, in the crystal, there are defects such as what they call is a stacking fault. There's also a thing called dislocation. And those things become important. As you can see, this is kind of an example of a perfect stacking, because where there is stacking fault, I think we have some data. One, as we expect a perfect lattice that's going in parallel, some places it becomes different. So those are called stacking fault. We'll come to that probably sometime. And there's also dislocations. That means the lattice plane takes off in a different direction. So, and there is screw dislocation, meaning that lattice plane suffers different kind of, defects. So all of those things become important, and we can quantify that because it's measured in scale. Therefore,
second question, real quick.
yeah.
How is a scientist to quantify aluminum as a dopant or element in a lattice versus maybe some other element?
Yeah. So the doping again is a high temperature treatment, which is if you have a wafer, you put inside the oven, the furnace, and then you evaporate the aluminum, and then let it diffuse inside the substrate. And they use different kind of sensors, but they have a way of measuring. I believe one way of doing it called, well, I get to look it up into it, but they have a way of controlling the concentration.
Yeah, no worries about that. But there was a slide with nickel and aluminum in a medium. How is a scientist with this instrument to know that is aluminum in the medium?
So this is not aluminum. This is
Next slide.
This one.
Yes. Oh, so it's a nickel ceramic. Sorry about that.
Right. So this white things is alumina, meaning aluminum oxide. So that's an inert material, not a metallic material. So you see this white thing is substrate is an alumina, Al2O3, right?
Okay.
Al3O2, alumina. And then there is a metallic layer, it's hardly visible from here, but this electrode is copper. And then there's another layer of alumina spray deposited, and then the top layer is nickel. So this is a kind of a messy system, if you can think that way. We have a paper on this one. I don't know if I shared that with you.
Yeah. The question on the previous slide was about the element. Maybe it was the following one.
Yeah.
That one here. Yeah. Back one more. that here, how the atoms shown in the lattice here uh, were unclear to someone looking at it. What is the statistical measure, or is it radius or diameter of these spheres to know it is aluminum?
You mean this inclusion here?
Yes. Or the one on 129.
Yeah, or this one, yeah. These are all the inclusions. And the objective was not to characterize them because they couldn't be anything else but alumina. In
Okay.
the system, there is only those two things are there. So it has to be either alumina or nickel.
Okay.
So now we if obviously someone can ask the question of purity or impurity of the alumina or the nickel, etc. The main project was not geared towards those kind of things.
Okay.
Its main objective was here to figure out, it's a spray deposition process. So what happens is they have this rod, and then they use a flame to evaporate the metal. And then it's called flame deposition. Is something I think is in the paper that you can probably look at it. I don't know if I shared with that. I'll make sure that I share this with you too.
No worries. Thank you.
No, sure. The spraying process makes it a messy system. So it's not like this is a pure nickel, right? This is a pure strip of nickel, metallic nickel. So this is not messy, but this guy, pretty messy system. So that's why we see that, this, even at the interface, the alumina and nickel is kind of intermingled, mixed up. So when you do the lattice imaging, then it shows we wanted to isolate the nickel area, but they are there. The alumina is there.
Yeah.
Everywhere the alumina is this one, this over here, this over there, this. So they're there. So what we did is we isolated some area where alumina is not there, so that we can just study the nickel lattice. So when you do an experimental investigation, that's why it's called an investigation, right? We do the investigation, meaning that you have to go back and forth and do a lot of other things to arrive at the, almost like a detective, except in a different way. So, that's very good question, and that kind of question should help you to go to the right direction.
Right. Thank you.
Absolutely.
Uncle, is the substrate also alumina?
Mm-hmm.
That's the lattice dilation?
This one?
Dilation. I think so, the before one.
So yeah, the dilations are measured here.
Yeah.
And this lattice deformation is happening because of the alumina inclusion in the nickel. So, for example, you see when the nickel is embedded, when the alumina is embedded within the nickel, then the nickel lattice has suffered distortion. In other cases where alumina is not all that pretty either. So both of them, when spray deposition is happening, as they spray the liquid, the flame evaporated material, then they go and stick onto the surface, and then they freeze into structure. That gives this kind of messy system. So there's always at the interface, it is they did a pretty good job actually, given the system is so messy. Nonetheless, they have clearly defined layers of nickel alumina, copper on top of this rod. So again, the whole purpose of that sample is totally different. Okay, we're not talking anything about why did they make that system. Oh, so our purpose is now, can we, with our T-ray technique, can we characterize it the way that makes sense and it produces information? Okay, any other point? Don't be shy. All questions are important. So we stop here for today and we'll pick up from here next time, right?
Yeah.
All right. Very well.